Look at this bicycle. This can be considered as a beam. If you look at the wheels, this wheels can be considered as two reaction points, and then the frame is a kind of like a beam. It is actually a beam. So let's simplify this and try to give make an example of this bicycle as a beam, shear force, and bending moment diagram on a bicycle. So let's go draw that. So let's make it simplified. Imagine that the weight of the bicycle frame, the entire frame, is uniformly distributed. So that's my imaginary frame or beam, which is uniformly distributed. The frame weight, assume that it is distributed at 2 pounds per foot. Every foot you have 2 pounds. And then in the middle section, because of this middle triangle, you have a little bit more weight. Assume that you have about another 2 pounds per feet there in the middle section. So that's the bicycle body weights, and it is carried by these two wheels. Let's assume that this is point A, reaction at A, reaction at point B. And then assume that this side is the handle. So on the handlebar at a random time when you're riding the bike, let's say you have 50-pound foot. And then assume that this is the pedals where you apply about 100 pounds force on a random time. And this is the seat. Let's assume that about 150 pound is applied on this seat. So all of this weight has to be carried by this bicycle frame. Assume that this is about 1 foot, this is about 1.5 foot, this is 1.5 foot, and that's 1 foot. So that's the situation. So we have simplified this bicycle beam. Now let's calculate. So that's the step number 1. Draw the free body diagram. Step number 1 is the free body diagram. So for this bicycle problem, we have drawn this free body diagram. Now step number 2 is to find the reaction forces at each of these points. So reaction forces at each reaction points or reaction forces. So the only way to calculate the reaction forces is to take moment with respect to A, and everything is static here, nothing moving. We are only solving this problem for one snapshot of the bike ride. Assume that this is the distribution. Of course, we can change this load around. We can apply the all forces at the seat point, and we can solve for that. So this is an assumption of, say, at a random time this will be the loading situation on a bicycle. So if I take moment with respect to A for that 50-pound load, which is about 1 foot away from point A, and which is a clockwise moment, which is negative, and then I got another 100 pounds from 2.5 feet, and then I got another 150 pound from 4 feet from A, and then I got 10 pounds of the distributed load, this one. So 2 times, so this bottom triangle, bottom uniform load would be 2 times the total, which is 1 plus 1.5 plus 1.5 plus 1, which is 10. And this uniform load would be 2 times 3, which is 6. So and both of these load acts from the middle here, so we don't have to consider twice, but if we want, we can do this like this. So 10, that is acting how many, 2.5 feet from A, and then minus that 6 feet is also 6 pound is also acting 2.5 feet from A, and then plus the reaction at B, which is 5 feet from A is equal to 0. Then if we solve for RB, which I have got 188 pound, we can apply the moment at B and then solve for RA. I have found that 128 pounds. So that's step number 2, find the reaction forces. Now I'm going to do the step number 3, which is the points of interest. So what are the points of interest? So anytime, maybe we can do it here. So step number 3 is the points of interest. Points of interest. Points of interest basically are the change of load. So whenever we have a change of load, that will be a point of interest. So here, start from A, I see a change of load here at 50 pounds. Let's define that's D. And then change of load here at the 100 pound, let's say that is E. And then change of load here at 150 pound, say that's F. So in this case, D, E, F are my point of interest. Also another point is the maximum moment point. Maximum moment points where basically shear force is 0. So at shear force 0, that is another point of interest which we will find after we draw the shear force diagram. So from the shear force diagram, so we'll have to wait for that maximum moment point. So points of interest are D, E, F. So we have to now cut at each of these point of interest and find the internal shear force and bending moment. So step number 4 would be cut at each point of interest plus find the internal shear force and bending moment. Internal shear force plus internal bending moment. The only thing external going on here is the load of the rider and the force that the rider is applying on the handlebar and also on the pedal, and of course the bike body weight, which is minimal, but for the sake of showing the calculation we're going to include that in here. So moment. Alright, so first we have to cut at D. Because D has a concentrated load, we have to cut before and after D. So let's cut before D. If we cut before D, it's gonna look like this. So because we cut before D, we'll not see that 50 pounds load. So we got here the reaction force 128 and this uniformly distributed load 2 pound per feet. And then we have to balance it. Whenever we cut it, we have to balance it. So at point D, to the left side of point D, downwards, and then by balancing this by a shear force downward, we are creating a moment or couple. So we have to counteract with this balancing internal moment. Now to find shear force, we have to do summation of Fy, all y-axis direction forces upward positive is equal to 0. So we can say plus 128 minus 2 times 1 foot. So we get 2 every feet and I got 1 foot of that load, minus VDL is equal to 0. So I found VDL is equal to 126 pounds. Now let's cut after D. if we cut after D, then we'll see that 50-pound handlebar force that the rider is applying on the handle. Everything else is the same. Only thing we have changed is we cut after D. So here is D point. So now we'll see that 50-pound force on the handlebar. So at D point, to the right side, downwards, moment, anti-clockwise, counter moment, internal moment. Now solve for V, the shear force, equal to 0, all upward positive, like that. So plus 128 minus 2, which is the uniformly distributed load, minus 50 minus VDR is equal to 0. So the shear force at D, to the right side of D, is 76 pounds. Now let's find the moment. Let's take moment at D, summation of all moment, sum to 0, then 128, which will make a clockwise moment, times 1 foot away from D, that 2 pound uniformly distributed load will do a counterclockwise, so that's positive, and that is 0.5 feet away from D, plus that internal balancing moment, everything is equal to 0. So MD is equal to 127 pound-foot. So you have found the moment at D. Now let's find the moment at E. Let me find that calculation page. So we're going to cut at E. So let's cut at E. Because we have a concentrated load at E, we have to cut before E and after E. So before E, we have that 50 pounds load here, and because we are cutting before, we're not going to see that 100-pound loads that was from that paddle force that the rider is applying. Then the E to the left side, downwards, M, E, and clockwise. The summation of all moment y direction positive is equal to 0. So you can say 128 plus minus 50 minus 2 times 2.5, that's 1.5 feet, minus, and then we got another uniformly distributed load here, which is 2 pound per foot times 1.5 feet of that load, minus E to the left side, shear force to the left side, then VEL was calculated 70. I'm not going to show you all that, so I'm going to just write VER. I calculated negative 30 pounds. And then the moment was calculated as ME was calculated 236.5 pound-feet. You also have to cut before and after F. If you do that, I calculated that is so before E, before the point F to the left side, that was calculated as negative 33 pounds, and then after right side of F was calculated negative 186 pounds, and then the moment at F was calculated 187 pound-foot. Now let's draw the shear force and bending moment diagram. We have all the information available, so let's draw the shear force and bending moment diagram. To do that, I need to draw that whole thing again. So that's my bicycle. The entire body weight is uniformly distributed like that, and then I have this middle section a little bit heavier, which has also load like that, and then this is, let's draw these reference lines. It's the middle here where the pedal is. So these are my reference lines. Now at the middle here we have that 100 pounds pedal force. At the seat we have 150 pound force. At the handlebar we have 50 pound force, and then this is 2 pound per foot. This is also 2 pound per foot. Now let's say make this is a shear force diagram. Shear force diagram. Now the reaction force here was calculated as 188, I think, yes, and this one was calculated as 128 pounds. So the shear force here would be, let's assume that this is 128, so shear force would be 128 here. So the curve's gonna go up like that, and then right before, so this is my point A, this is point D, the middle is point D, this is F, and this was B. So right before D I had I think 126 or something. So it's gonna go drop like a straight line like this. It drops another 50 here, so it goes like that, 50 drops, and then right before D it was right after D, I think it was 70. Let me go, didn't write all those numbers. So 50 drops, and then here right before E it goes to 70 here. Let's say this is 70, and then here at this point you got 100 drops, so it's gonna go drop 100, and that was then 70. Let's say that's 30, and that's 70 is kind of definitely not looking scale. So it's gonna drop 30, and then it goes here like this, and then 150 drop again here. So this 150 drop here like this, and then slide drop here. This thing is definitely not drawn to this scale. So I think this was 188, this was something I can't remember what was that, 186. So this was 186. So the shear force diagram is, this is the shear force diagram of this bicycle problem. Should have written all those numbers in one page. And this is the bending moment. Let's draw the bending moment diagram. Now whenever I say shear force and bending moment, they are all internal shear force and internal bending moment. All right, so at point D, let's see what we got at point D. Okay, so moment at point D was calculated 127. Calculated that at 127 right here. Moment at E was calculated 236. Let's assume that is here. They're all kind of second degree curve, and then this was something like 186 or so, and then go like this. So this was 127, this was 236.5 pound-feet, and at point E, I think it's 187. This value is 187. So basically the highest stress will be at the pedal or the bottom bracket where this thing might fail. So that's it about this problem. Let's